Alright everyone, welcome to another Physics QBits video. Today we're going to be talking about some of my advice for solving problems involving pulleys. For this video, we're going to assume all of our pulleys are massless, and so this will be kind of the introductory pulley video, and then the next video I release will be about what happens when we add mass to our pulleys. But for now, we'll kind of work on the, the first semester version of a pulley problem. And so the first thing I want to talk about is what actually a pulley does. So pulleys are like ropes, right, that have, pulleys are wheels that usually have some rope passed over them. So we have a rope right on one side coming off the other. And for example, a setup might be, we are pulling on this side of the rope, right? And there's a block that we're trying to lift on the other side of the rope. And so the actual action of a pulley is to change the direction of a tension force. So pulleys allow us to redirect tension. What I mean is, right, if we look at the tension force that's actually being applied to the pulley on the left-hand side, so the one we're yanking on, right, the tension force actually goes down and to the left. This is what we might call TL, or tension on the left-hand side. And the tension on the right-hand side is now rearranged such that it points upwards, right? And so we can transfer this kind of downwards, leftwards pulling into an upwards pulling on the other side of the pulley. And so what that means, right, is that the pulley is kind of transferring some of this TL into a TR on the other side of the pulley. And so this leads us into our first piece of advice. When we're talking about massless pulleys, we can immediately write down a simplification. Okay? Whenever you see the phrase massless pulley, what this means is that the tension on one side of the pulley is always equal to the tension on the other side of the pulley. There's a couple ways you can kind of think about this. The first is if we just use Newton's second law on the pulley, right? We imagine there's some net force on the pulley, and that's causing the pulley to accelerate. If the mass of the pulley is 0, and I solve for the acceleration, well, then I'm going to get that the acceleration is F net divided by the mass of the pulley. I'll even index this with a little p. Right? This tends towards infinity if I make the pulley mass smaller and smaller. And so the problem is we can't have any imbalance of the left or right tensions, right? We need these two to exactly be equal so that we don't have a pulley that has an infinite acceleration. There's another way you can think of this that's a little bit more hand-wavy. So for those of you who are experts, by the way, and want to tear me a new one, I am fully aware of how hand-wavy this is, okay? And I'm trying not to give myself whiplash from how hard I'm waving my hands. The intuition is that if the pulley has no mass, right, you can kind of transfer all the force on the left-hand side to the right-hand side for free. In other words, none of the force has to go into kind of rotating the pulley, right? The pulley is free to rotate. And so in this way, you can also imagine the tensions on one side are equal to the tensions on the other side because the transfer of forces here is perfect, right? And so, like I said before, this is kind of an imprecise explanation, but I think this intuition is a useful one for solving pulley problems. In any case, whenever you see the phrase massless pulley, you can always write down that the tension on one side is equal to the tension on the other side. Okay, so for the rest of this video, what I wanted to do was kind of talk about the rest of my pieces of advice in the context of a problem. So let's do this simple kind of example problem and see what other kind of wisdom we can pull from it. And so in this problem, what we have is two blocks attached to each other by a rope, and that rope is being passed over a pulley. One of the blocks on the left-hand side is sitting on a frictionless table. And so what's going to happen is as this block kind of falls on the right-hand side, right, the left block is going to accelerate with some particular acceleration value. The right-hand side block is just hanging there, and so we're going to have some like gravitational force pulling on it, right? And that's the thing that's going to cause the system to kind of move over. And so our goal is going to be finding the acceleration of the hanging block, the blue acceleration AR. The first thing I want to say is that pulley problems really are just force problems, right? The thing that a pulley does is transfer one direction of tension into another one. And so what we should do is start off with a free body diagram like we do all force problems. And so for the block on the left, the one that's sitting on the table, we have a gravitational force, right, with a value of ml times g. We know that there's going to be a normal force from the contact with the table, right? So we have some Fn on the left, and we know that there's going to be some tension in the rope pulling this object to the right, right? And so we can call this TL, for example. For the other object, for the mass that's just hanging, mr, we know that there is a gravitational force pointing down. We have mrg. And we have the tension pulling up from the string, right? So we have tension R like this, okay? All right, so with these free body diagrams, right, the usual prescription is to write down our Newton's second law equations associated with each of these free body diagrams. So the thing I'm going to say right now is that because we know that all the motion for the left side block is just kind of left to right, I'm going to forget about doing the vertical forces. I'm just going to sum the forces in the x direction. And then similarly for the right-hand side block, we know everything that happens here is up and down, right? So I can just do the kind of up and down forces. And so normally when we go from the free body diagram to the Newton's second law equations, right, we think about establishing a coordinate basis where the usually what happens, right, is anything going to the right and upwards is counted as a positive force or positive direction. And anything going to the left or down is negative, right? This leads us nicely into advice number 2. Let the pulley dictate the positive and negative directions. And so what I mean is instead of using this coordinate system, right, it turns out this coordinate system actually can get you tripped up in a lot of cases. What I like to do is decompose the problem in such a way that any direction that's associated with the pulley rotating in this direction is positive, and anything going the other way is negative. So, for example, if I want to write the Newton's second law equations for my left-hand side block, ML, the one in red, right, the tension is pointing to the right. Rightwards here is associated with a clockwise rotation of the pulley. And so I'm going to call this force positive TL. And by Newton's second law, we know that because this is the only force in the x direction, this had better tell us what the x acceleration of the left side block is, right? Similarly, I can take a look at my free body diagram on the right-hand side, and I can notice that in this case, downwards corresponds to positive, right? Because the gravitational force is the same direction as the one that causes the pulley to rotate clockwise. And so when I set up my Newton's second law equations here, I'm going to have a plus mrg, because this is the positive direction, right, for the pulley. And the tension force is actually going to be in the opposite direction. So I have a minus sign associated with this guy. And we can write down the right-hand side of our Newton's second law. This is going to tell us what the acceleration of the right-hand side block is. And even just to keep things consistent, I'm going to get rid of this little x subscript so we can see the labels here are the same as in the problem. Okay, and so these are our two equations. And if we look through this, what we find is that there are a few too many, or I think there's one too many unknown here, right? We don't know what the tension on the left is. We don't know what the tension on the right is. We don't know what the left acceleration is, and we don't know what the right acceleration is. And so what that means is we need some constraints, right? That's our kind of natural next step here. So I'm going to write the constraints here. This is a little out of order, I'm sorry, but let's think about these. Okay, so the first thing we can notice is this is a massless pulley, right? Oh, I should have said that, but this is a massless pulley. And so, like we said before, right, this means that whatever tension is on this side of the pulley, it has to be the same as the tension that's on this side of the pulley. And so our first piece of extra information is that TL must be equal to TR, right? So let's just call this thing T. And so what that means is in our equations, right, we can simplify them such that we get rid of these subscripts on the tensions, and we've reduced one of the kind of degrees of freedom here. The other thing we know about pulleys, and this leads us into advice number 3, is that you can usually you can relate A1 and A2. So because these things are attached by a rope, right, the usual kind of rope constraint holds, and we know that the acceleration on the left-hand side has to be the same as the acceleration on the right-hand side, right? We're not kind of bunching up the rope so that one of them moves at a different rate. And so we can write down that AL is also equal to AR. This is really convenient because we can then define just one general acceleration as A, and that'll be the acceleration for both of these objects. So we can, once again, get rid of this, and I'll change this color to red so we can see they're the same, right? Now, Presumably, if I've done my constraints properly, we should now have a solvable system of equations. And so if I take a look here, now we only have one unknown tension, right? This uppercase T, and we only have one unknown acceleration. And now we can just solve these equations. Okay, so what I'm going to do is then I'm going to copy this equation. And let's put it here so that we can actually solve it, right? So here's our final set of equations. And I'll label them equation A and equation B. And what I'm going to do is recognize that equation A is basically solved for me, right? I just know that whenever I see a tension, I can replace it with ml times A. And so if I substitute into equation B now reads mrg minus, and the tension is this mla, right? So mla is equal to mr times A. And so now the goal is to solve for the acceleration, right? We know that this red A is the same as this blue A because both of these things accelerate at the same rate. So all I need to do is solve for this A now. So what I'm going to do is add MLA to both sides, and I'm going to work out the rest of the problem in just one color ink, since it'll get a little cumbersome otherwise. So we have MRG remaining on the left-hand side, and our right-hand side now reads MRA plus MLA. Then what I can do is recognize that because A appears 2 times here, I'm going to factor it out. So I see that I have one term that says A times now the sum of MR and ML equals MRG. Okay, so now I can divide both sides by MR plus ML. And I recover the final result that the acceleration is equal to MR over MR plus ML times G. Like this, right? Okay, and so this is our final result. We can see, right, of course, that if MR is really, really large compared to ML, so let's say MR is like 1,000 and ML is 0.1, then this answer just tells us that this system basically free falls, which is good, right? On the other hand, if I make ML really, really large, like if ML is like, you know, a train hooked up to a cardboard box full of feathers, the acceleration is going to be very small because the numerator is going to be much smaller than the denominator. On the other hand, if ML is very large, so for example, if I hook up a box of feathers to a train, then I know that the acceleration should be quite low, right? Because the weight of the box of feathers, this MR times G term, is not going to be able to overcome the inertia of the combined system MR plus ML. All right, so let's move on to a quick summary of what we talked about in this video. So first, we found that pulleys change the direction of a tension force, right? Change direction of a tension. And so, for example, right, if we have a pulley here, and we have a rope slung over the pulley, and there's 2 things attached to each side, right? We know that there's going to be some tension on the left-hand side of some value, and a tension on the right-hand side of some value associated with the ropes on either side, right? And so the first piece of advice we talked about for solving pulley problems was looking out for this key phrase, massless pulley. Right? The massless pulley assumption tells us that the tensions on the left-hand side and the right-hand side have to be equal because of that kind of acceleration argument we made earlier. The second piece of advice we ran into is to let the pulley dictate which direction is positive and negative when you're going from the free body diagram to the Newton's second law equations when you're solving the actual problem. So when going from FBD to Newton's second law, let the pulley dictate positive, negative directions. So for example, in this problem, right, the thing that we did was we said, well, we know that the pulley can only rotate clockwise or counterclockwise. So any kind of force or direction that's associated with clockwise, we're going to call positive, and any direction we're associated with counterclockwise is going to be the negative direction, okay? And this helps you keep track because what's really happening is this kind of usual coordinate system, as it goes over this pulley, is getting rotated the same way the pulley is kind of rotating our tension force, okay? And the last piece of advice I have for you is keep an eye out for the kind of equal accelerations constraint, right? We know that if this rope is taut or the string is taut, then whatever acceleration is happening on the left-hand side has to be the same as the acceleration that's happening on the right-hand side, right? We can't have the rope kind of bunching up at one side of the pulley. One side cannot accelerate faster than the other one, in other words. And so usually you can write the constraint that AL equals AR. So this is another useful thing to look out for when you're doing the constraints part of solving a force problem. This has been kind of short, but this is really all I have to say. These pieces of advice can really make it, I think, a lot easier to solve pulley problems. So if you struggle with these, try kind of injecting some of these ideas into your solution method, and hopefully you'll find that it helps keep some things a little bit more clean. Okay, that's really all I have. As per usual, if you have any questions or thoughts or any kind of problems you want to challenge me with, you can leave those in the comment section down below. And don't forget to like and subscribe for more free physics problem-solving tips and tricks. This has been Physics Tutoring Quantized.